7.6 is solving exponential and logarithmic equations. This first video is going to be just focusing on exponential equations. So I'm going to come back to the logarithmic definition, but an exponential equation, of course, is an equation in which the variable expressions occur as exponents, and I think you know that. So if I had, 2 to the x equals 5, that would be an exponential equation. Logarithmic equation is an equation that involves logarithms of variable expressions. So if I had log base 2 of x equals 7, and you had to figure out what that is. So just a property that I think you're familiar with, but just in case, if b is a positive number other than 1, then b to the x equals b to the y if and only if x equals y. And of course, if you think about that in terms of a problem, if you have 5 to the x equals 5 to the 4th, you know x has to equal 4, because 5 to the 4th is 625. So the only way for this equation to balance out is if you stuck a 4 in there and they equaled each other. So that means x has to equal 4. Okay, so this first example says solve 64 to the x equals 16 to the x plus 1. So if you remember the exponential base rule, if the bases of 64 and 16 were the same, then their exponents would have to equal each other. Clearly they are not the same. So lucky for us, 64 and 16 are both powers of 4. So if I rewrite, 64 is really 4 cubed, and that's still to the x power. 16 is really 4 squared, and that's still to the x plus 1. So again, I didn't change the problem because 4 cubed is still 64 to the x, and 4 squared is still 16 to the x plus 1. Then you know power on a power, I distribute, so 3x, 4 to the 3x, and then I'm going to distribute the power of 2 here, so it's going to be 4 to the 2x plus 2. Easy to remember, or easier to forget to distribute that all the way through, so be careful. And now my bases of 4 are the same, which means my exponents have to be the same. So I can just say 3x has to equal 2x plus 2. And of course I can subtract 2x, and I get x equals 2. Now just like with previous chapters, we have to check our answer because it could possibly be extraneous. And you can just mentally check that. But remember to go up to your original equation and check it. So if I do 64 squared, I want to see if that's equal to 16 to the 2 plus 1. And yes, 64 squared equals 16 cubed, so it works out. So make sure you check it. This next one says solve 6 to the x equals 27. So you could estimate it. You know that 6 to the first is 6. You know 6 squared is 36. So it's somewhere in between 1 and 2. Probably closer to 2, so like 1.8, something like that. However, that's not going to cut it, so you have to algebraically find that exact answer. So I cannot make 27 a power of 6, and I can't make 6 a power of 27, and 6 and 27 don't share any powers in common, so it's not quite as straightforward as the last example. So when you're stuck in exponential form, like I don't know the exact answer, 6 to the what equals 27, then flip or switch to logarithmic form. So this is called, I call it logging both sides. So if you think about the base of your exponent is 6, so why not log base 6 both sides? It's kind of like dividing both sides by 5 or multiplying both sides by 5 or something like that. You're going to log base 6 both sides. And of course you have to do log base 6 to both sides so that it balances out. So again, 6 to the x equals 27 was my original, and I log base 6 to both sides, so that's legal. And then you know from your inverse properties that log base 6 of 6 cancels out, so you'll just have x. And you also know from your change of base that you can do log or natural log of 27 divided by log or natural log of 6, and then when you dump that on your calculator, you get 1.0 0.8394, etc., etc. Again, make sure you check it. So if you take in the original equation 6 raised to the 1.8394 blah blah blah, you'll get approximately 27. Okay, this last one has a base of e, so that's always fun. 6 times e to the 0.25x plus 8 equals 20. So if I kind of highlight the fact that here's my exponent, everything else around there I can get rid of, right? So I want to isolate, get it in exponential form, isolate that exponent. So of course I would subtract 8 first. So 20 minus 8 is 12, and then I can divide by 6. And 12 divided by 6 is 2. Now that my exponent is isolated, I can't really guess what x is. That would be hard to do with the base of e. So again, I'm stuck in exponential form, so I switched to logarithmic form. Now I could definitely log both sides, but since my base is e, I would either want to log base e both sides, or if you recall, the natural log has a base of e. So I'm going to natural log both sides. So if I natural log both sides, I have to natural log the right-hand side to balance out, of course. Remember that the natural log has a base of e. Not that you're ever going to see it there. I'm just going to toss it in so that you can see that the natural log base e cancels out e. So I'm just left with 0.25x. And then the natural log of the natural log of 2, I would dump that in my calculator, which I'll do in a second, and that's approximately 0.693, etc., etc. And then last but not least, I'm going to divide by 0.25. So now I would go to my calculator, and if you're dumping things on your calculator, I would wait till the very end to dump that on my calculator just so that it's as exact as I can keep it. So the natural log of 2 divided by 0.25, and I got 2.77, etc., etc. And then last but not least, don't forget to check it. So again, going back to my original equation, if I type all of that into my calculator, replace the x with 2.77 approximately, I will get 20. Again, keeping in mind that because I rounded my answer here, when I check it up here, it's going to be very close to 20, but not exact, and that's okay because of our rounding.